and cook in the same way that huevos rancheros doesn't exist in nature. It has to be put together.
Paul's lab is like a dieter's kitchen, satisfying a hunger for powerful magnetic crystals while reducing the amount of neodymium needed in the recipe.
Hold on, did he say huevos rancheros?
Fresh batch.
He was comparing it like, hey, you don't have this finished meal or dish recipe in nature. You got to take all the ingredients. What goes into huevos rancheros? Anybody know? Anybody know what it is? So it's like a breakfast. I guess I've never had it, but I looked it up because I was curious. So you start with a corn, like tortilla flatbread thing, and then you put like a fried egg on it. And they do, I hear you can do chili on it, or you could do like guacamole or other things, but it's a breakfast dish. Yeah, kinda, yeah, like a breakfast taco, sure. Huevos rancheros, cool. So he says in a similar way, these type of magnets that they're making don't exist in nature. They're having to build them.
The main ingredient is ordinary iron. Iron makes magnets. There you go. But adding neodymium makes magnets on steroids. Here's how you make a magnet. First, all the solid ingredients are sealed into a quartz tube to be melted together.
David Pogue, scientists.
After some time in the furnace, tiny magnetic crystals formed in the melted iron.
2,000 degrees. Oh my God. It's like threading a needle.
The next step is to separate the solids from the liquid.
Dump it in, slam the lid.
They put the centrifuge on the floor for safety, in case anything goes wrong with the super hot vial.
We turn it off, let's open it up, and we can take it out. We have single crystals of the neodymium iron boron separated from the extra liquid, which the centrifuge separated with the 10 to 100 Gs.
The result of all this cooking and spinning? A powerful magnet that uses less neodymium, we hope. It sounds like you're saying you're trying to use as little of the rare earth as possible.
Absolutely.
Why? Because I thought rare earths aren't really that rare.
The rare earths are not rare, but they're hard to separate, and that's part of the expense.
Even with Paul's help, it looks like rare earths are going to remain in short supply, at least for now. Partly because scientists continue to find surprising new ways to use these strange metals. Like marine biologist and conservationist Patrick Rice. If he has anything to say about it, rare earths may be coming soon to a fish hook near you.
Is this your little kiddie pool where you bring the children to swim? This is our little tank here where we have a couple little bonnethead sharks and a little nurse shark in here.
Okay. Bryce was searching for the next great shark repellent when he made an accidental discovery that looks like it'll be good news for both man and fish.
We had sharks in a tank like this, and a pump broke on one of our tanks. And so we were playing with these magnets, and we put the magnet down by the tank to go fix the pump. And when we put the magnet by the tank, the sharks took off.
Somehow, the sharks inside the tank sensed the presence of magnets outside the tank. And when they did, they voted with their fins. Patrick offers to demonstrate the weird repulsive effect. He hands me a case of super strong magnets.
So this is full of actual regular old refrigerator. Oh, yeah, more than refrigerator magnets. That's right. That's right.
And you're saying that this will somehow repel the sharks.
And here comes a little guy.
That's a little nurse shark. It might work for him. Tell me
Okay, 3, 2.
All right, now, the first time I watched this, admittedly, I was like, it looked like he just hit the side of the tank, but he actually does stop the magnet case before it hits. So the sharks are somehow detecting the magnetic field.
2, 1.
Oh my God! You dropped that thing on his head.
Yeah, you saw it, huh?
Yeah. He's like, somebody goes, wow!
Right.
What's that?
Right, exactly.
The shark can't see the magnet, but it obviously feels the effect. And it's not happy.
1, 2, 3, now. Boom. Got it.
Really?
Yeah, you got it.
That's crazy.
Amazing.
Patrick thought he could somehow use this effect to save sharks from being inadvertently caught by commercial fishermen. But there was, so to speak, a catch.
We put the magnet right above the hook on the line.
Oh, okay.
And what was happening was the hooks were swinging around and getting caught on the magnets. So it wasn't catching any sharks, but it wasn't catching anything else either.
But he wasn't willing to give up. He decided he needed to find the weakest possible magnet that would still affect sharks. The first step was to create a baseline for comparison by exposing sharks to non-magnetic materials. He offers to recreate his experiment.
You know, I don't have insurance for this.
Be careful, it might be slippery.
You're warning me about the slipperiness? Dude, there's 3 sharks in here.
No, but they're nice.
Yeah, just want to say for the record that I'm standing in a tank full of sharks.
That's correct.
This is like Jaws 7, the kiddie pool.
Before I have to ask the question, raise your hand if you have seen the original Jaws movie from the 70s. Okay, good number. Okay, and then the rest of you have not. Those that have seen it, should everyone see Jaws at least once?
Yeah.
No? Why not? It's not good. You don't like it? Did you see it? You saw it? You didn't like it? Okay. How many of you saw it and did like it? Okay. You all think it'd be worth a watch? Okay. I agree. So I would also recommend, if you haven't seen Jaws, the original Jaws movie, there's several, but yeah, watch it. It's a good classic.
Step 1, capture a shark.
Dude, you just caught a shark with your bare hands.
Then flip the shark upside down, which induces a trance state called tonic immobility. Once the shark is calm, we test its reaction to a piece of ordinary, non-magnetic lead.
Would you like me to just honk her on the head with this?
See, he's at it again. It's like Sid. Cruelty to the animals now, not just toys. You know, from Toy Story?
Yeah.
It's terrible.
Rub your eyes.
So it's not a visual thing.
Using a shield to make sure that the shark can't see the metal, I bring it close.
No reaction.
None at all.
As expected. Next, a non-magnetic piece of samarium, a rare earth element. The expectation was, because it's non-magnetic, there would be no reaction.
Oh man,
She doesn't like that at all.
this is like kryptonite for sharks.
Yes, it is.
Wow, that's amazing. It woke her up and drove her crazy.
Yep.
So the idea is you could make what out of this stuff?
Well, the idea is that it's not magnetic, so we could potentially incorporate it into a fishing rod. And then you have something that repels sharks, but it doesn't have the magnetic properties, so it won't tangle the gear and stuff like that.
The discovery that non-magnetic rare earths have a repellent effect on sharks was a complete fluke, and it works with other rare earth metals as well. But why? What do sharks have against these particular elements?
We believe it's creating a little electric shock.
A little electric shock.
Yeah,
A
yeah.
shark shock.
Shark shocker.
Patrick demonstrates using a beaker of seawater, a piece of samarium, a voltmeter, and an actual shark fin.
Bum, 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 bum.
When he submerges the samarium and the shark fin in the seawater, an electric current flows.
Whoa! Oh my gosh!
That's almost a D-sized battery.
Did we just make, in effect, a battery?
Correct.
As a group, the rare earths give up their outer electrons very easily. In salt water, samarium atoms break free of the metal disk and give up one or more of their outer electrons. The atoms become positively charged and are attracted to the shark fin, which, like many biological materials, has a slight negative charge. The movement of the charged atoms creates an electric current,
Wow, that's some real juice flow.
just like in a battery.
It is like a battery. It's a complete closed circuit, and the voltmeter's measuring that. That's pretty amazing.
But is the effect actually strong enough to put a
All right, pay
shark
attention.
off its meal?
So we've just done our little test.
There's one final experiment we can run to find out.
What we're going to do now. You're welcome.
That's just for the blooper reel. We like to kiss it.
As I was saying, there's one final experiment we can run to find out.
What we're going to do here is a little experiment we've never done before.
You haven't done this before?
I haven't done this
You
before.
waited till there was an actual TV camera rolling?
There's a 9-foot lemon shark in this lagoon.
Now, guys, I'm not like a shark nerd. I'm not really into sharks, but this lemon shark, I think they call it a lemon shark. This is really pretty. The way it moves, it's really beautiful.
And it's lunchtime. Now for the test.
This side over
We're going to suspend 2 identical pieces of tuna. One will hang below a piece of lead. That's our control. The other under a piece of samarium.
You go ahead and put it out there.
Really?
Yep.
Lower down.
If the test is successful, the shark should avoid the samarium-tainted meal but not near the lead.
Here she comes.
Well, she didn't like it at all. She was aiming right at it, and she was like, oh!
That was an excellent response. Notice the other fish doesn't have any effect on them.
Hey, wait a minute. Now she's going for the lead.
So there's the control.
And she loves the lead one.
No problem on the controls. That's awesome.
Since making this remarkable discovery, Patrick has experimented with designs for shark-repelling fishing hooks, and he's seen some promising results.
Last experiment we did, we put out 46,000 hooks, and we reduced shark bite catch by 27%.
Get your precious jump here.
Shark zapping is just the latest entry in a growing list of curious rare earth abilities. But perhaps the real shocker is that these 15 elements were so long misunderstood, their identities masked by their identical outer electron shells. But those aren't the only atoms hiding from view. Scientists now know that most elements come in more than one version. The different versions are called isotopes. Consider carbon.
Okay, so in your notes, here's the first thing, I think, main thing for the notes today. Isotopes are versions of elements, versions of atoms based on the number of neutrons they have. So he's about to tell us all about carbon and the fact that it has 3 naturally occurring versions or isotopes for carbon, and each one has a different number of neutrons. So yesterday we put ions in our notes, and those are either positively or negatively charged elements or atoms. These are different in the number of neutrons, whereas ions are different in the number of electrons. Make sense? Cool.
Backbone of life. It has 3 natural isotopes or versions. Each has 6 protons and 6 electrons. That's what makes them all carbon. The difference between them is the number of neutrons in the nucleus. Neutrons are electrically neutral particles that act as glue to hold atoms together. What we think of as normal carbon is called carbon-12, 6 protons plus 6 neutrons. But about 1% of carbon atoms have an extra neutron, giving them 7. They are called carbon-13. And about 1 in a million have 8 neutrons. That's carbon-14. And that rare version of carbon has proven to be a crucial tool for unlocking the past.
Okay, so carbon-14, put it in your notes, carbon-14 is the version of carbon that is radioactive. Carbon-14, the one that has 8 neutrons, carbon-14 has 8 neutrons, and it is radioactive. It is not stable. It is going to decay over time. And if we know the decay rate, we can do some math and figure out how long ago different living things died. Got it? Did you write that down?
Carbon-14 is radioactive.
It sure is. All right, here we go.
Several times a year, scientist Scott Stein travels to the shores of Mono Lake near Yosemite National Park.
Then is Mono Lake.
Say again. Oh, yeah. Gosh, I forgot about you. Glad you remembered.
Little Lake, yeah, right here at the foot of the Sierra Nevada.
He's studying the long history of droughts in California, trying to determine how frequently they occur and how long they last. Over the millennia, the water level has risen and fallen as the area has cycled between wet periods and dry times.
So that sandy area should be the level?
During times when the climate was dry, Little Lake dropped down, exposed the shorelands, and allowed trees and shrubs to grow.
When the dry periods ended and the water level rose, the trees drowned,
The 28th.
marking the end of the droughts. Since then, the remains of those trees have been well preserved by the arid climate.
These droughts were long, persistent.
To determine how long ago these droughts occurred, Scott is using carbon-14 to date the trees. Unlike the other natural isotopes of carbon, carbon-14 is unstable. Over time, its atoms begin to deteriorate. One of its neutrons turns into a proton and spits out an electron. Now with 7 protons instead of 6, it's turned into nitrogen. That process is called radioactive decay, and scientists know exactly how long it will take for half of any amount of carbon-14 to decay away.
All right, there's the next thing for your notes. What the heck is half-life? Half-life refers to the amount of time. So half-life is an amount of time, specifically that it takes for half of a sample of radioactive isotopes, so some parent isotope, the unstable one, the radioactive one, to decay and become a daughter isotope. So in this case, the parent isotope is carbon-14. It's radioactive. It's unstable. And the daughter isotope is nitrogen. So the nitrogen is more stable, and we refer to it as the daughter isotope. Don't get mad at me for calling them parents and daughters. I didn't come up with that, but that's the convention. Okay? Questions on that? So a half-life is an amount of time. It's specific to the isotope. So, for example, carbon-14 has a half-life of, I want to say, 5,730 years, if I remember right. And then others, like potassium to argon, I want to say that was like 1.3 billion years. Don't quote me on that. I haven't done it since last year, so I may have gotten that wrong. But they have very different amounts of time that it takes for them to decay.
Scientists call that time its half-life. Living things constantly replenish the carbon in their bodies. Animals from food, plants from the atmosphere. But after death, that process stops. The amount of carbon-12 stays the same, but the carbon-14 decays away at a constant rate, making carbon-14
That was kind of cool, right?
an atomic clock.
I'll see that again.
To know how carbon-14 decays away at a constant rate, making carbon-14 a ticking atomic clock. To know how long ago this ancient tree died, we just need to count the carbon atoms in a small sample. Piece of cake, if you're this guy.
Now, these are fragments of the tree stumps at Mono Lake, and I understand that you are the master of carbon dating.
Physicist Tom Brown works in the carbon dating program at Lawrence Livermore National Laboratory.
In fact, if I'm not mistaken, carbon dating actually pre-existed before internet dating. Very much.
Carbon-14 can be used to date samples up to 40,000 years old. It's been used to find the ages of many Egyptian mummies and other ancient artifacts.
So how does wood fare with carbon dating?
Intact wood is a very good material to do. It retains the carbon from when that material died, and we're able to extract it, purify it, and it's a really good material for dating.
Tom needs only a small amount of wood. Even this tiny sample is overkill. The lab technician cleans it and reduces it to a fine powder.
Oh man, this huge thing? This is your carbon dater-matic 3000?
The actual counting of the atoms takes place here in the carbon dating accelerator.
I see you bought the camping version.
We have our 1 milligram of carbon from the wood chip sample basically in that hole.
In that tiny little hole?
That's where the 1 milligram of carbon is from that sample.
Not a lot of wood chips.
And we put about 64 of these holders in one of these wheels.
The accelerator applies a powerful electric charge to the atoms, basically lightning, giving them the speed and energy they need to hit a detector with enough force to be counted.
The ratio of the carbon-14 ions, the amount of carbon-12 in the sample, tells us how old the sample is.
The fewer the carbon-14s, the older it is.
Yes.
With his accelerator, Tom calculates that our tree died about 150 years ago. That must have been when California's last drought ended, a key piece of information for understanding the region's climate cycles. Carbon-14 has helped open up deep insights into the past, but it's just one of hundreds of radioactive isotopes, that is, elements that decay. In fact, at the bottom of the periodic table, beginning with number 84, polonium, all of the elements and their isotopes are radioactive, including the element that stands for both the promise and the peril of radioactivity, uranium. 92 protons, 92 electrons, and 146 neutrons. Before the nuclear age, uranium was thought to be the end of the periodic table.
It was.
But in the last 70 years, scientists have left nature behind and created 26 new elements. The age of man-made atoms began in the first half of the 20th century, when researchers began bombarding elements with neutrons. Sometimes the neutron is simply absorbed, creating a new isotope. But sometimes the nucleus can't take the punishment. It becomes unstable and splits into
two smaller atoms. Okay, so that is fission. F-I-S-S-I-O-N. Put that in your notes. Nuclear fission is the splitting of an atomic nucleus. So we mentioned nuclear fusion within stars, how you take atomic nuclei and fuse them together to make heavier elements. Here, you're taking a heavier element and splitting the nucleus in two to make lighter elements. Nuclear fission, splitting of an atomic nucleus. So here you had uranium split, and the result was a lot of energy, krypton, and barium as a result.
smaller atoms in a powerful reaction called fission that releases large amounts of energy. To learn more, I've come to the Nuclear Museum in Albuquerque, New Mexico.
Yeah, this is a mad science project.
Where atomic scientist Matt Dennis has offered to demonstrate how a nuclear reactor works.
You guys make a lot of jokes about gone fission. I actually have an atomic shirt that says something to that effect.
I knew that! I knew that! Okay, now, to the naked eye, this looks exactly like a nuclear reactor.
The similarities are the mouse traps are uranium atoms, and the white ping pong balls are neutrons, which you use one to start a chain reaction.
In a reactor, one neutron splits a uranium atom, which releases energy and 2 or 3 more neutrons, which in turn split more atoms, releasing more neutrons, and so on, causing a chain reaction.
So you get more and more neutrons, and thus the chain reaction keeps going.
All right, ladies and jelly spoons, here goes the orange ping pong ball. This evening's role, you'll be portraying the neutron. All right, I just drop it in here.
You just drop it in right there, and we'll start the chain reaction.
Incoming neutron! I'm sorry, Matt. The camera wasn't rolling. Can you set that up again?
From a single neutron, an escalating response. Our mousetrap reactor doesn't have many atoms, so the reaction dies quickly. But pack enough fissionable uranium atoms closely enough together, and the whole thing can get out of hand pretty fast. And sometimes that's the point. This museum has the world's largest public collection of artifacts that chronicle the dark side of nuclear energy.
And so that's a Triton C3 up there.
It's huge. You guys are just surrounded by bombs. I feel like a kid in a death store.
In 1945, the U.S. developed 2 atomic weapons. Both were used against Japan. The first was fueled by an isotope called uranium-235. That bomb was called Little Boy.
This is the Little Boy bomb. This is the very first.
I guess I shouldn't bump it then, huh?
Well, it's a concurrent copy. This is just like it. And inside this big case was a gun barrel and high explosives on the ends to push the 2 pieces of enriched uranium together at supersonic speed.
The military made only one uranium bomb, because separating rare U-235 from the more common U-238, which doesn't work in fission reactions, is a very difficult process. So for the second bomb, called Fat Man, they used an entirely different element, plutonium. 94 protons, 94 electrons, and 150 neutrons.
Put it in your notes. Plutonium was the first man-made element. So they kind of did it by accident. Took them a while to realize what they had done, but then it became useful for weapons-grade fuel. nuclear fuel. It is a very easily, it's a good material to do fission with, yes. Okay, it'll dry. Just like open the pages up as best you can so it can dry. All right, ready? So plutonium, first man-made element, cool.
Plutonium was the first man-made element. It was first created as an accidental byproduct in the first nuclear reactors, but no one knew it until plutonium was identified in 1940 by chemist Glenn Seaborg when he bombarded uranium atoms with protons and neutrons until some of them stuck. Over his long career, Seaborg went on to isolate or create 9 more man-made elements, including americium, which is in minute quantities in the smoke alarms in our homes. He pushed the end of the periodic table all the way to element 106, which is called Seaborgium in his honor.
I started out here at the laboratory using these counters quite frequently.
Ken Moody is a chemist at Lawrence Livermore Lab, but he developed a love of big, fat, juicy atoms as a graduate student in Seaborg's lab in the 1970s. Afterwards, his first job was analyzing radioactive debris produced by underground nuclear weapon tests.
And it was our job to go pick samples and tell the physicists how well his devices work.
You're smart enough to know that those fragments would probably be radioactive.
Yes.
Would they not be dangerous?
Well, we didn't carry them around in our pockets.
Since the end of the Cold War, Ken's goal has been to expand the periodic table. He's teamed up with a Russian lab, and together they've succeeded in creating 6 new elements in this cyclotron. But there's a hitch. They've only made a few atoms of each, and they're all so unstable, they decay away almost as soon as they come into existence.
With all due respect, none of the 6 elements that you've discovered are actually in the world right now.
That's correct.
So, do they count?
Doesn't sound like much, but for a chemist, a 10-second activity actually allows you to do something with it, but it isn't enough that you could put it in a bottle and put it on the mantelpiece and admire it the next day.
Still, Ken has high hopes for the future. He believes that somewhere beyond today's largest man-made elements, scientists will find an island of stability on the periodic table, where some super-large atoms will be both stable and useful, perhaps satisfying the needs of our future civilization. It's amazing to think that something as complex as the physical universe can be put on a single chart. And from about 90 basic elements, man and nature have teamed up to create the incredible variety of stuff in our lives. And the story is far from over. As scientists continue to hunt the secrets of the elements, what new understanding and technologies will follow can only be imagined.
All right, don't act like you didn't enjoy it at least a little bit.
I like
Not the worst, huh?
I like it on the lake.
The lake?
Yeah, you tripped off the rock.
Oh, yeah, yeah. I think they were at the ocean, but
And it exploded.
yeah. Okay, cool. So have your notebooks open. We're going to do a couple of things. We are going to look at the first type of model that we're going to make, an electron configuration model. It's called the Bohr model, named after Niels Bohr. You don't have to know that, but dude won a Nobel Prize, so pretty smart guy. And Bohr models, but it's in your notes, Bohr models show the electrons on their energy levels. So we make a series of concentric rings, and sometimes you'll hear them referred to as like orbitals or energy levels or just rings.
What is that?
Take your pick, huh?
Second word.
It says show electrons on the energy levels or on the orbitals or on the rings. So it'll be the easiest to teach it just by like doing it and showing you how, okay? So first off, we've got hydrogen here, symbol H. So you put the symbol in the middle and then find hydrogen on the periodic table. I'll get you guys one for your own copy, but right now we can use the one on the back wall. Where is hydrogen? At the top, in the top row, okay? So if we look at rows going down, hydrogen is that very first top row. So it's the first row. So So it gets one ring. First row, it gets one ring. So would helium. And then how many electrons, I mean, unless it's an ion of hydrogen, how many electrons does hydrogen have? Just one. So we're going to throw one dot at the top of that ring in our model. And we're done. That's it. That is a Bohr model of hydrogen. Okay. How about carbon? Find carbon on the periodic table. It's kind of in the middle-ish, slightly to the right. Second row. Do you guys see it? Okay, so how many rings am I going to have around the symbol? 2, because it's in the second row. So go 1, 2. And how many elements are in the first row? On the first row, you've got hydrogen and helium, so 2. So if there's 2 elements on the first row, how many electrons do you think would go on the first ring? 2. Max 2 on the first ring. You'll never have, as a Bohr model, you'll never have more than 2 on that innermost ring. Well, if you've got 2 electrons there, how many will go on the second ring? Huh? Just 1?
2.
2?
3.
Let me ask you this. How many electrons total does carbon have? 6. So if we've got 2 on there already,
4.
we'd need 4. That's done for carbon. That is the Bohr model for carbon. All right, now how about we try magnesium? Find magnesium. It's toward the left. Atomic number 12. You guys see it? Mg. Okay, so what do I need to do for a Bohr model for magnesium? 3 rings, because it's on the third row. How many electrons go on the innermost ring? 2, right? None of them would have more than 2. There's 2 elements on the first row, so we put 2 electrons on our first ring. How many elements are in the second row of the periodic table? 8. So we can put up to 8 on this next ring. So we've got 2 and 8 makes 10. How many are left? 2, because magnesium has 12 electrons. So that would be, say again? Oh, I thought you said something. So you'd have, that is the Bohr model for magnesium. Depending on your chemistry teacher next year, they might have these grouped in like pairs of 2 on the Bohr model. I don't really care. All right, I'm going to do a different thing for you. All right, I'm going to put a question mark for a symbol. So you're going to see if you can figure out what the element is based on my drawing of the Bohr model for that element. Okay. What is it? It'd be helium. 1 ring, so it's on the first row. 2 electrons, it's helium. See how that works? All right, so how about, what's that? What? Lithium, yeah. So first row is full, hydrogen, helium for the inner row. Next ring, lithium has 3 electrons. So 1, 2, 3. Good. How about, give me a moment here.
6 or 7 more.
It is chlorine, Cl. Everybody see that? Any questions on that? Okay. Now, in the previous section of video that we watched, I think it was yesterday or the day before, we saw that, well, Cl really has one spot open, doesn't it? What do I mean by that, one spot open? Have you guys ever heard the term valence electron or valence shell before? Yes? One or two of you? So put this in your notes. Valence means outermost. Okay? So the valence shell is this one on chlorine. It's the outer shell.
What is the valence shell?
The valence shell is the outermost shell. It's the one on the outside. By the way, they're the most important because those are the electrons that interact with other atoms' electrons. They're on the outside. So chlorine has a spot for one more valence electron. Does that make sense? Sodium is the one they used the other day. Remember the popcorn? Right? So sodium, Na, how many shells would it have? How many rings? 3. Because it's in the third row. And it would have the innermost shell full with 2. And it would have 8. And then how many are in the third?
2.
Look at the periodic table. Okay, so I'll just tell you then. Sodium is number 11. And yeah, it's atomic number 11, yeah. Okay, so it's atomic number 11, and it's the first in that row. So it's just got 1. It's got 1. So because 2 and 8 is 10 plus 1 to get to 11. All right? Now, chlorine needs 1 to fill its valence shell. How many does sodium need to fill its valence shell? 1? Well, it already has 1. 1 more would be 2, which would be how many shy of a full 8? 6 more. So here you'd need 7 more, right? To get to 8, to have a full valence shell. Well, let me ask you this. Would it be easier, do you think, to gain 7 more electrons or to just get rid of this one? If you got rid of that, wouldn't you drop back?
Yes.
And this would be your valence shell, and it's already full. So what's going to happen here is sodium, that 1 out there, is going to get given away, and chlorine will be happy to take it. At that point, both have a full valence shell. But because it's picked up an electron, it has a negative charge. And because sodium lost an electron, it has a positive charge. So that's why they form an ionic bond together. Are we out of time? 2 minutes, so why are you putting away your stuff? You guys know the rule, 1 minute. 1 minute, okay?